That's tough. Yeah.
Because I'm just kind of tough here trying to get a job that'll easily work. And you're like, okay, I can leave at 3:30
Yeah.
on like two different days.
You'd have to still work at like 5 o'clock in the morning.
Yeah. There's just one place, because I went in and then I had my interview, and I honestly got nervous. And they had me sit down and start doing stuff on the computer.
Uh-huh.
I got nervous and I just like, my brain just stopped working. And I was like, okay.
Oh man.
They were like, when you come in and like you're more comfortable with because it was SolidWorks, but I didn't touch SolidWorks in a minute.
Uh,
And then it was also, they have 2010 SolidWorks. So I was like trying to find stuff and we were telling me to do stuff.
oh man.
And
The
then just-
interface is all different, right?
Yeah.
Oh,
it
man.
was not where it was used to it being. And then they just told me like, once it's more familiar to just come back.
I see.
So then like watching videos from like 2010 SolidWorks, just like,
Uh-huh.
because they were pretty open about me just like either like adding an extra hour onto a day or just to like balance it out so it would work with the next closer level.
Okay,
But
that's pretty cool. That's pretty.
I emailed the owner of the company again.
Uh-huh.
He's the one that told me to reach out again. So like,
Okay, that's good. That means they like you.
yeah. We'll see.
That's great. Where's the company at?
It's in Irvine.
Okay, oh, that's great.
Yeah, they
Great
do,
area.
like 5-point axis CNC parts.
Oh wow,
So
that's cool.
yeah. And he was like showing me, he was like on the computer showing me like where they like sent their like parts off to me.
Yeah.
It's like a ton of different random applications.
Hmm. How'd you find that opportunity?
It was on Indeed.
Hmm. Man, the landscape of like job hunting nowadays is like so different from when I was like in your guys' shoes. It's yeah. Before like that was like the very early days of like LinkedIn. When I was, but now LinkedIn is like LinkedIn's like kind of like old school now. No one really uses LinkedIn anymore.
I don't, LinkedIn helps definitely. Cause I've gotten a couple offers out of the state,
Uh-huh.
but I wanted to get my master's. So just see what- if it comes back around, then we'll see.
Mhm. Gotcha.
But it's definitely useful when you like go on and you see someone working at the place you want to work at that has like, oh, you both like, attended Cal State Fullerton.
Uh-huh. Oh, that's
Okay.
true.
That's what I kind of did. I went to spam message all the people working at SpaceX that either went to Fullerton or there's any connection. Because once you start putting stuff, it just like relates. Or it's like you have like a shared connection.
I see.
With someone.
I see.
Like, oh, you know this guy, I know him too. Like, how's it work? How's it at SpaceX?
Uh-huh.
I'm trying to weed my way in there.
I see. SpaceX is cool. They do so much cool stuff with SpaceX.
They all told me the same thing. Like half the time, they just don't even look at like application or a resume.
Yeah.
There's so many of them.
Yeah.
It's like,
It's disheartening, but at the same time, like understandable, I
Yeah.
guess. But, yeah. Because like there's some opportunities you feel like, you'd be a great fit for, but then they don't even look at your resume. Like that's, kind of deflating. All right, it's 5:30. Let's go and get started. All right, good evening, everyone. How's everyone doing today? Doing good, doing good. Okay, so today we're going to continue on with our discussion of 2D finite elements. And so today we're going to start getting into the nitty-gritty of doing calculations. All right. So I have two kind of big sets of lecture notes left for the course before we finish out. There's this section here which I'm hoping to finish within a lecture or a lecture and a half. And then the next section, which is kind of the big one that's relevant for your project, it's called isoparametric elements. Okay. So I'm going to try to finish everything up, maybe by the lecture after the exam, just so that you'll have everything that you need for the final project. I'm hoping that the entire last week of the semester, or at least the last lecture of the semester, will mostly just be just kind of free office hours time, so you can kind of work on the project and kind of get feedback from me. Okay, but that's kind of where we're headed. We have kind of one set of lecture notes here. It's kind of medium length, and then the isoparametric elements lecture note. That's kind of the length here. Okay. All right. So remember, our midterm exam is a week from today, so it's going to be next Thursday. So I posted the solutions for the homework. That you can find those on Canvas. So if you go to the page for week 13, you'll see it posted there. And remember, the midterm is going to be primarily based on that. Okay. All right. Any questions I can answer before we get started for today? Okay. All right. So let's go ahead and get started. So on Tuesday of this week, we introduced the concept of 2D finite elements. And so we did just kind of a very brief review of the vector calculus and kind of the geometrical concepts that we need to know. Today, we're actually going to put it in practice. So we're going to actually form element stiffness matrices and such. Okay. But also, like I mentioned on Tuesday, that because of the complexity of the structural mechanics equations in 2D, basically just mostly just because they are vector equations, we're going to shift our focus to heat transfer. Okay, because the nice thing about the heat equation is that it's a scalar equation, so we only have to solve for one unknown. Okay, so the title for this set of lecture notes is 2D heat conduction with finite elements. Okay. So just to kind of remind you, we are working on a two-dimensional domain, okay? And we don't have to be particular about the size or shape of the domain itself. So if we draw kind of an arbitrary potato like this, okay, right, where the interior of the domain is given by our symbol omega. And the boundary of the domain, remember, the boundary consists of the line that kind of goes around the entire boundary. Okay. This is given by delta omega. So this is the boundary of the domain. Okay. Which is a line. Okay. So the main thing I need you to remember from this, and so we drew this figure on Tuesday as well, is that an important aspect of the boundary in 2D problems is the outward unit normal. Okay, so at any point on the boundary, you can draw a vector, okay, like these, and these guys right here are the outward unit normal. Okay. And the purpose of those outward unit normal vectors is to specify the direction that goes outside of the domain. Okay. So that's going to be important when we specify our Neumann boundary condition. Okay, so with that said, with our domain and our boundaries defined here, we can write out the strong form for the 2D heat equation. All right, so logically, we're going to progress in the same way as our 1D equation. So we're going to start with the strong form. Where from the strong form, we're going to derive the weak form. And then from the weak form, that's going to form the basis for our finite element form. Okay. So let's start with the strong form. So this is the classical form of the Laplace. Basically, it's called the heat equation, but in math terms, it's called the Laplace equation. Okay. So we have K. K here represents the thermal conductivity. We have partial squared T, partial x squared, plus partial squared T, partial y squared, plus S of x comma y. So S of x comma y represents our thermal generation, and all that's equal to 0. Okay. So S here, this is our thermal generation term. Okay. Eventually, that thermal generation term is going to make it into our element forcing vector. Then we have K here, which is the thermal conductivity. Of course, like we talked about last time, this is a partial differential equation because we have derivatives in multiple different directions now. So not just x, but we have a y dimension. Okay. Let me give you the shortened version of this. So what I've shown you there is kind of the full, what I think of as kind of like the full version of the heat equation, which has all the partial derivatives written out. But the shorthand notation is a little bit more convenient to write. So the shorthand version of this, we make use of the operators that we learned last time. So this is K times the Laplacian of the temperature T plus S of x comma y is equal to 0. Okay. Remember, this operator here, this is the Laplacian. And basically, it basically says that if you have a Laplacian, you just take second order derivatives of the quantity with respect to each spatial dimension, and you just add them together. Okay. So that's the strong form for the main governing equation. Let's talk about the boundary conditions now. So if you recall from our 1D situation, the Neumann boundary condition on the heat equation is called a heat flux. So let's look and see what the heat flux boundary condition looks like in 2 dimensions. Okay. All right. So heat flux, we didn't really talk about this much in 1D, or I may have mentioned it, but heat flux basically just represents the situation where heat or thermal energy is either exiting the domain or entering the domain at a particular location. Okay. So it looks kind of like this. So let's say that we have a 2-dimensional boundary like this. Okay. So this line right here represents delta omega. Okay. And so if we have a heat flux boundary condition, basically that represents the fact that heat is traveling across this domain. All right, so let's assume for a second that to the left of this line, we have the interior of the domain, okay? And so if the heat is, if the arrows are going from left to right here, this represents a case where the heat is leaving the domain. So we have an outward heat flux. Okay? So we have an equation in heat transfer that describes this. Okay? And so the equation in heat transfer is called Fourier's law, which says that the heat flux across a surface, okay? So we'll use the symbol Q double prime here. This is equal to minus K times the partial derivative of the temperature field in that direction. Okay? So in this particular example, let me kind of make that clear. This is kind of a specific case. Okay? We have the outward heat flux here, where the outward heat flux is going in the x direction. Because in this case, our boundary is vertical, and so our heat is going horizontally across that domain. Okay? So Fourier's law in this case would be heat flux is equal to minus K times partial T partial X. That's for this particular case because the heat is going in the x direction. Hence, we take the derivative in the x direction. Okay. Now we can generalize this, right? So in a general 2D case, we're going to have situations where the heat is traveling, not just across the x direction, but maybe we have a horizontal boundary, so the heat's going in the vertical direction in that case, right? Or if maybe we have an oblique boundary, maybe something like this, right? Like a slanted boundary, and we have heat traveling across this boundary like this. So we have heat that's traveling across, right? The most important thing to note here is that what's important is whether the heat enters or leaves the domain, right? And so to track that, we're going to look at the component of the flux that's going perpendicular to the domain surface. Okay? Because any component of heat flux that's parallel to the surface is not going to leave the domain, right? And so we only care about the component that's coming out or going in. Luckily, we have something there to help us with this. Okay. Right. So in a two-dimensional case, remember that for every boundary, we are also tracking the outward unit normal. Okay. What do you notice about the direction for the outward unit normal and the heat flux in this case? They're parallel, right? And so the outward unit normal, its main use that you'll see is to basically allow us to formulate heat flux boundary conditions for heat that leaves or enters the domain. So we can definitely make use of this. And so the general form for the heat flux boundary condition is given by the following. Okay, so we have Q double prime. We'll put a bar over it. Q double prime, 2. Okay. We have minus K. Right? K, remember, is our thermal conductivity multiplied by quantity. We're going to take the gradient of the temperature field. Okay. Remember what the gradient represents. The gradient is a vector which shows the partial derivatives of temperature in every direction. And we're going to take a dot product with the normal vector. So this quantity right here, this quantity of the dot product of delta T dot N, okay, this gives us the component of the temperature gradient that's perpendicular to our boundary. Okay. So this will work, this form of the boundary condition will work, no matter how our boundary is oriented. All right, and you'll see this show up in our weak form in a second. All right, any questions on this? Okay, good. All right, so now that that's out of the way, so now that we have the heat equation itself, I should have blocked this up here. Okay. So that's our governing equation, as well as the mathematical form for the Neumann boundary condition. We're now ready to state the weak form. Okay. So just to kind of remind you, the way that we obtain the weak form for the strong form is that we first multiply the strong form by a weighting function. Our weighting function in this case is going to be a function of x and y. So it should have the same functional dependence, our solution, t. Okay. So in 2D, t is a function of x and y. So that means our weighting function must also be a function of x and y. Okay. Okay. Then what we're going to do is we're going to integrate the entire equation and then use integration by parts to shift some of the derivatives around. Okay. All right, so let's look and see how this is done. Okay. So of course, to do the integration by parts, we need to make use of Green's theorem, okay, which we kind of briefly went over at the end of class last time. Let's go through the process. All right, so I'm going to start with the shortened version of the heat equation. So I'm going to say our heat equation is going to start with K Laplacian of T plus S of X comma Y is equal to 0. Okay. First thing we're going to do is we're going to take this entire equation and multiply it by the weighting function. Okay. So weighting function is going to be a function of x and y, w x and y. Okay. And then I'm going to take this entire equation and then we're going to integrate it across our domain. Okay, so we're going to do a double integral over A. Okay. All right, so let's go ahead and simplify this. And so I'm going to distribute, first thing I'm going to do is I'm going to distribute that weighting function to every term. And I'm going to distribute that integral to each term as well. So we can integrate both the Laplacian term and thermal generation term separately. Okay, so we have double integral on A, w of x and y, times k, Laplacian of t, dA, plus double integral of A, w of x and y, s of x and y, dA equal to 0. So that right there, that's our result of this. We just, all we did was we multiplied by the weighting function and then we just performed our integral there. Okay. All right, so the next step is we're going to take this integral here on the left. And we're going to apply integration by parts, right? Because you can see here we have a Laplacian. So the Laplacian is roughly equal to a second order derivative. And then on the other hand, we have our weighting function w, which has no derivative. Okay, so we're going to use integration by parts to kind of shift these derivatives around. And because it's a 2D case, we're going to do integration by parts using Green's formula. Okay. So let's go ahead and do that. Okay. So according to Green's formula, we use integration by parts. This integral here is going to split up into two. Okay, so the first integral that we're going to get is a line integral. So this is a line integral around the boundary of our domain, okay, times w of x comma y times k times the gradient of t dot product with the normal vector ds. Okay, this right here is a line integral around the boundary. Okay. That should look very familiar, or the interior of that integral should look very familiar to you. It should look very similar to our heat flux boundary condition, but we'll deal with that in a second. Minus our second integral, which is our balanced integral term. So we have double integral on the domain A of gradient of W multiplied by K times gradient of T dA. Okay. This right here is our balanced integral term, or balanced derivative integral. And then this other integral here, the integral on the thermal generation term, there's not much else we can do with that term. So I'm just going to bring that one down. Okay. So this is plus double integral on A, W of x and y, S of x and y, dA. Okay. And of course, all this is equal to 0. Okay. So we're going to make one more substitution before we box this. Okay. Actually, let me highlight this more effective. Okay, so if you look at this term right here, Sure, I'm highlighting in green right there, okay? If you look back to our strong form of the equations, you'll see that that term, that k times the gradient of t dot product with the normal vector, this is exactly the same as our heat flux boundary condition. Okay. So what I'm going to do for this term right here, so let's sub in heat flux at the Neumann boundary. And we gave that the symbol Q double prime with a bar on top. Or we're going to do minus that. Okay. And so if we plug that in and then we kind of shift some things around, we move the balanced derivative term to the other side of the equation, we end up with the following result. Okay. So our weak form is the double integral on A of the gradient of the weighting function multiplied by K multiplied by gradient of T dA. Okay. Is equal to minus line integral around the boundary of W of X and Y times Q double prime with a bar ds. Okay. That's our heat flux boundary condition that we just plugged in. Plus double integral on A of W of X and Y times S of X and Y dA. Okay. And that is our weak form. So we went pretty fast through that derivation just because we've seen it a couple of times already in 1D. The only difference is that we applied kind of that special Green's theorem to do our integration by parts. Okay. All right. Any questions on that here? All right. So if we're going to look ahead a little bit, right? So this expression right here is going to form the basis for our finite element form, right? Hopefully you're starting to see some elements that are similar to our 1D case, namely what's on the left side of the equal sign. So that integral which has the balanced derivatives, that's going to form the basis for our element stiffness matrix. And then everything on the right-hand side of this expression is going to form the basis for our element forcing vector. Okay. But we'll get there all in good time. Okay, actually, before we move on to the finite element form, let me kind of highlight the fact that, remember, one of the requirements for our weighting function, so recall, so we require the weighting function to disappear at the locations of the Dirichlet boundary conditions. Okay, basically anywhere that we have a specified temperature boundary condition, our weighting functions are going to disappear in those cases. So, and disappear basically means that we set them equal to 0. Okay. All right, so that's kind of a quick rundown of the weak form. So let's jump into the finite element form. Okay, we're just kind of speed running things along here, right? So we did strong form, weak form. Now that we have the weak form, we're gonna do our finite element form here. Okay, and just to kind of remind you, the way that we go from the weak form to the finite element form is that we take all our weighting functions, we take all of our solution variables t, and we plug in expressions that involve the shape functions. Okay. So remember our shape functions, those are our functions n, okay, n1, n2. Now that we're in 3D, we're gonna have more shape functions than that. Okay. And so that essentially means that, oh, what happened there? Oops, okay, that was weird. Okay, so that means we're gonna plug in w of x and y is equal to w1 times n1 of x and y plus w2 times n2 of x and y plus w3 and 3 of x and y. Okay. Same thing for our temperature. So T of x and y, our solution is equal to T1 and 1 of x and y plus T2 and 2 of x and y plus T3 and 3 of x and y. Okay. For n1, n2, n3, those are our shape functions. And basically what they allow us to do is that they allow us to interpolate the solution on each individual element. Okay. All right. Of course, I haven't shown you what the shape functions look like in 2D. So if you remember in 1D, our shape functions were simple linear function. So we have x minus x1 or x minus x2 divided by x1 minus x2, and 2 is equal to x1 minus x divided by x1 minus x2. Okay. Of course, in 2 dimensions, they're not going to have these forms, so don't write them down. But I just wanted to remind you kind of what they look like. Okay. And so the first part of this section here, we're going to derive kind of what those shape functions look like in 2D. Okay. All right. So remember, those shape functions, part of what makes them shape functions is that they help our finite element solution satisfy, all the properties that it needs to. Okay. Because when you have a finite element solution, right? So you have a two-dimensional domain like this, right? What we're going to do from here is we're going to put a mesh on this domain. And so by putting a mesh on the domain, we're going to break it up into all these individual elements, right? Where that whatever expression that we get for the element stiffness matrix and the element forcing vector, we're going to evaluate it for each individual element. Okay? And so essentially, we're solving kind of each element kind of individually, right? But remember, each element, right? The solution for each element should kind of work harmoniously with all the elements around, right? Because when you put them all together, you should get one overall solution for your entire domain, even though we're solving it on an element by element basis, okay? And so what that basically means is that our solution must be continuous across element borders. So when you travel from one element to the next, your solution should stay continuous, okay? And this property right here, this requirement that our solution be continuous, this tells us what our shape functions are going to look like. Okay. Because think about the way that we're using our shape functions, right? Our shape functions are essentially being used now to represent our solution, okay? So basically the character of the shape functions is going to be the character of our solution as well, right? And so if we're going to require a property of our solution for the entire domain like this, then that's going to impose requirements on the shape function themselves, okay? So it's just like we did in 1D, but just kind of remind you about that process. Okay. Any questions on this part here? Okay. All right. So all this information here is pretty consistent with 1D, right? So we're representing our solution with shape functions. Those shape functions have to follow certain rules, and those rules are just meant to make sure that our solution is nice and continuous and smooth. Okay. Unlike 1D though, when you get up to 2D finite elements, you actually start to get you start to get some choice in terms of what your elements actually look like. Okay. And so in 2D, we can actually choose the shape of our finite elements. Okay. Because in 1D, we had no options, right? So in 1D, our domain was just a line. And so if you were to break up a line into smaller lines, your elements are just smaller lines, right? And so we didn't really have any options for shape there. But in 2D, there's lots of different shapes. Okay. So for example, you can have a triangle. You can have a rectangle. Or just kind of the more official name is a quadrilateral. Technically, you can have things like pentagons and hexagons as well, and so those are all kind of valid shapes. But generally speaking, just because of the theory, for the most part, we stick with just triangles and quadrilaterals. Okay. But people have tried to do pentagons, hexagons, octagon shaped finite elements. There just really isn't a point to doing so. Okay. Yeah. Question.
I thought octagons didn't tessellate.
Yeah, you're right. Octagons don't. It is very hard to get a mesh with octagons. But mathematically, it is possible to have shape functions for an octagon shape. It's just that you wouldn't be able to get a mesh unless it's like a very simple, unless your domain was actually like an octagon. Yeah, but for the most part, we just have triangles and rectangles.
So the shape doesn't have to tessellate.
Technically, no. So if you're talking just strictly from the mathematical point of view, as long as you can form the shape functions for it, and your what's called, and your domain kind of supports that, then you can make any shape in theory. But how practical it is kind of another thing. That's why you don't see anything beyond quadrilaterals. So like hexagons, pentagons, those are kind of, they're fun math problems, but they're not very practical at all. Okay, so for this class, we're going to focus mostly on triangles. I'll mention quadrilaterals a little bit, just because it's, it is a main one. But we're going to keep the theory kind of as simple as we can, especially considering how much time we have left. So let's go over the very classical kind of 3-node triangle element. Okay. All right, so the 3-node triangular element looks like the following. So as the name suggests, it's a triangle with three corner nodes. Okay. So just to keep things consistent, let me label the nodes. So we'll label the nodes 1, 2, and 3. Okay. And then additionally, we can specify the coordinates for each of the nodes. So we have x1, y1 for node 1. For node 2, we'll have x2, y2. And node 3 will have x3, y3. So all the physical coordinates for all of the nodes are known. Another thing that's known for about each of the nodes, because this element is going to be part, or because the shape is going to be part of a finite element solution, we also know the nodal solution values of each of the nodes. Okay? So we have T1 at node 1, T2 at node 2, and T3 at node 3. Okay? So T1, T2, and T3, these are the nodal solution values of each of those nodes. Okay. All right. So one thing that you'll start to learn in 2D and 3D is that however many nodes that you have in your element, that's how many shape functions you're going to have. Okay. And so for a 3-node triangle, we're going to need to solve for 3 shape functions. Okay. Another important thing to note about this element is that it is a linear element. And so that means our overall, evolution function t is going to be a linear function of x and y. Okay. So that means our temperature t. Okay. Right. We know that this is already equal to T1 plus times N1 of x and y plus T2 of x and y plus, or T2 times N2, excuse me. T2 is the nodal solution value, N2 is the shape function, plus T3, N3 of x and y. Okay. But if it's a linear function, we also know that it's equal to the most generic kind of linear function in 2D. So that's going to be A0 plus A1x plus A2y. Okay. Where whatever the values are, or how we solve for the values of A0, A1, A2, okay? When we solve for these constants, that's going to give us eventually our expressions for the shape functions. Okay. All right. So how do we solve for these constants, right? Let's go back to our requirements on the finite element solution. So remember, our finite element solution is required to be continuous and smooth across element boundaries, right? If you think back to how we accomplished this in 1D, we accomplished this by requiring that our expression here, our polynomial, matches the nodal solutions at the locations of the nodes. So our nodal solutions being T1, T2, T3. Okay. So when we evaluate this T function at x1, y1, which is the location of node 1, it should equal to T1. Same thing when we evaluate it at T2 or at x2 and y2, that should equal to T2. And when we evaluate it at x3, y3, that should give us T3. Okay. So that's going to give us three equations that we can solve this, use to solve for the three unknowns here. Okay. Okay, so let's go ahead and write that out. So T of x1 comma y1 is equal to a0 plus a1 x1 plus a2 y1. Okay, this is equal to T1. Okay, we evaluate T at x2 comma y2. Okay, it's equal to a0 plus a1 x2 plus a2 y2. This must be equal to T2. We evaluate everything at x3 comma y3. We get a0 plus a1 x3 plus a2 y3. And that's equal to T3. All right. So of course, this is it's possible to solve this. It's three linear equations and three unknowns, right? The unknowns being a1, a0, and a2. Okay. So we're not actually going to solve these by hand, but just know that you can solve these for those unknowns. Okay. Okay. And then solving for those unknowns, what we're going to do is you're going to rearrange the equation to make it similar to up above. Okay. And so our form is T of x and y is equal to T1 n1 plus T2 n2 plus T3 n3. Where n1, n2, n3, those are going to be functions of x and y that you're going to obtain, from this result. Okay. All right, so if we do that, we get expressions for our shape functions. We get the following. Okay, so n1 of x comma y is equal to 1 divided by 2a. Okay. So that a on the bottom right there, that is the area of the triangle. This is multiplied by x2 times y3 minus x3 times y2 plus y2 minus y3 times x plus x3 minus x2 times y. Okay. That is the first shape function. Second shape function, n2 of x and y is equal to 1 over 2a, where that a is still the cross-sectional or the, the area of the triangle. And this is multiplied by quantity x3, y1, minus x1, y3, plus y3 minus y1, x, plus x1 minus x3, y. Okay. Remember these x1, x2, x3, y1, y2, y3, these are all the physical coordinates of each of the nodes. Okay. And then we have n3 of x and y is equal to 1 over 2a multiplied by quantity x1, y2, minus x2, y1, plus y1 minus y2 times x, plus x2 minus x1, y. Okay. So of course, these are a lot more, these are a lot messier, right? So they're not as clean as our 1D shape functions, but it's because we're in 2D. And so there's just a lot more constants, and a lot more things kind of floating around. Okay. If you look at the mathematical forms for these shape functions, you should see that they match our original functional form, which is a constant plus a term that's multiplied by x plus a term that's multiplied by y. Okay. And that's intentional, right? So whatever functional form that you started with, your shape functions are going to mimic that form. Okay. So these equations right here, these are the linear triangular, the shape functions for the linear 3-node triangle. All right. Any questions on this? All right. So those are the shape functions. So those are definitely good to note. Okay. Thinking ahead a little bit, just because we know that eventually we're going to plug this into our weak form. We know that the other thing we're going to need to find out are the derivatives of this, right? So we compute gradients and things like that. So let's compute the shape function derivatives. So we have quite a lot here. So we have three shape functions, n1, n2, n3. And each of those we can take the derivative with respect to x and y. Right? So we have six terms here. Okay. So let's do partial n1, partial x. Okay. So we're going to take the derivative of the first function there with respect to x. Most things are going to cancel out because we only have one term that's multiplied by x. And so that's y2 minus y3 divided by 2a. Okay. The next one we have is partial n1, partial y. This is x3 minus x2 divided by 2a. Next, we have partial n2, partial x. Okay. This is y3 minus y1 divided by 2a. Next, we have partial n2, partial y. This is x1 minus x3 divided by 2a. Okay. We have partial n3, partial x. This is y1 minus y2 divided by 2a. Then we finally have partial n3, partial y is equal to x2 minus x1 all divided by 2a. Okay. All right, it's a little tedious, I know. It's definitely not the most fun thing to write these down. A little bit of flashbacks from direct stiffness when we had all these kind of massive terms, but that's kind of what finite elements is. It's just a lot of kind of terms and a lot of formulas to but that's why we write computer programs to help us do this. Okay. So with this out of the way, let's go ahead and let's start plugging into our weak form with these expressions here. Okay. All right, so if you go back to the weak form, you will see that there are quite a few expressions that we need to plug in for, right? And so the first thing that we have to compute is the gradients, right? So you have gradient of W and gradient of T. Okay. Okay. So in this case, because we're doing scalar equation here, a scalar heat equation, that means our gradient of W is going to be partial W partial X, comma, partial W partial Y. Okay. And same thing with T. So T here, the gradient is going to be partial T partial X, partial T partial Y. Okay. Okay, so if we write expressions for partial W partial X. Okay. Remember the way that we formulate W and T, we formulate these in terms of the shape functions. And when we take derivatives of those functions, those derivatives just move straight to the shape functions. Okay. So partial W partial X is W1 times partial N1 partial X plus W2 partial N2 partial X plus W3 partial N3 partial X. Okay. Same thing with partial W partial Y. Okay. So this W1 partial N1 partial Y plus W2 partial N2 partial Y plus W3 partial N3 partial Y. Okay. We have basically the same thing for the temperature, so I'm not going to repeat. All right. And so we can put this into matrix form. Okay. Because hopefully you see we have a lot of similarities, right? So both expressions, because the W's, the W1s, W2, W3, those are constants, right? And they show up in both expressions. We can kind of make this into a matrix and make this a bit easier. Okay? So what we can say is that partial our gradient of W. Okay, gradient of W is going to be in this case, we'll call it a row vector, right? So we have partial W partial X, comma, partial W partial Y. Okay. Taking those expressions up there into account, we can say that this is equal to the row vector W1, W2, W3. Okay. Multiplied by this matrix, right? And this matrix is going to contain all of the shape function derivatives. Okay. So this matrix can be partial N1 partial X, partial N1 partial Y, partial N2 partial X, partial N2 partial Y, partial N3 partial X, partial N3 partial Y. And of course, we've already computed all the shape function derivatives. They are all up here. Okay, so I'm not going to bother plugging in from them, but we know that's what this is about. So let me go ahead and box this for now. Okay. Because what I'm going to do is I'm going to write out the similar expression for the gradient of t. Okay. So for the gradient of t, we're going to come up with a very similar expression for that. The only difference is that we're going to transpose it just so that we can form a matrix from it. Okay? So gradient of t, we're going to say is a column vector of partial t partial x, partial t partial y. Okay. But as a column vector, that means we're going to swap, we're still going to have the shape function derivatives. We're still going to have the nodal solution values. We're just going to swap their places kind of relative to the previous expression. Okay? And we're going to transpose it. Okay. So to get that same thing, we're going to have partial this 2x3 vector. Okay. We have partial n1 partial x, partial n1 partial y, partial n2 partial x, partial n2 partial y, partial n3 partial x, partial n3 partial y. Okay. And then we're going to multiply this by the column vector t1, t2, t3. All right. So all of a sudden, this became a huge mess, right? Well, you haven't seen the whole of it yet, right? Because now we got to multiply these two things together. Okay. So now that we have expressions for the gradients, we can plug this into our expression for the weak form. Okay. So recall weak form. Remember, our weak form had three integrals essentially, right? So we had the integral with the balanced derivatives. We have the line integral around the boundary. That's eventually going to become our norm and boundary condition term. And we had our integral on our thermal generation function. Okay. So let's start with the first integral first, just because we have the gradients here, right? So our first integral was double integral across the domain of the gradient of w multiplied by k gradient of t dA. Okay. We have an expression for the gradient of w. We have an expression for the gradient of t in terms of the shape function. So let's go ahead and plug all those in. Okay. Keeping in mind that the w's and the t's are all constants, and so I'm just going to factor those out of the integral. Okay. So let's plug in for gradient of w and gradient of t, right? So what we get from that is we get w1, w2, w3, okay, multiplied by integral for a. Okay, then we have our 3x2 vector, so we have partial n1 partial x, partial n1 partial y, partial n2 partial x, partial n2 partial y, partial n3 partial x, partial n3 partial y. Okay. So those two quantities together, the w's and the shape function derivative, that corresponds to the gradient of w. Okay. We have the thermal conductivity K that's multiplied in the middle here. We can't forget that. Okay. Then we're going to start to plug in for the gradient of T. Okay, so the gradient of T, we're going to plug in this expression up here for that. Okay. So that's our 2x3 matrix. So we have a partial n1, partial x, partial n1, partial y, partial n2, partial x, partial n2, partial y, partial n3, partial x, partial n3, partial y. Okay. Multiplied by the column vector t1, t2, t3. Okay. Which again are constants, and so we're not going to worry about that. Okay. Right. So it's a lot of matrices already, but we haven't even gotten to the fun part, which is multiplying these two together. Because when we multiply those two matrices of the shape function derivatives, everything with the partial n, partial x, partial n, partial y, we're going to end up with a 3 by 3 matrix. Okay? So multiplying these two. Okay? And so that 3 by 3 matrix is essentially going to become our element stiffness matrix. Okay. All right. So there's no easy way to do this. We're just going to have to write it all down. Okay. So that matrix is going to be over here. All right. So it's going to be 3 by 3, but it's probably the ugliest 3 by 3 matrix I've ever seen. So let's just do it. Okay. So of course, to get this matrix, you're going to do a matrix multiplication of this, which is going to every term or every entry in this matrix is going to involve the product of shape function derivatives plus something. Okay, because it's a 2 by 2. We're multiplying a 3 by 2 matrix by a 2 by 3. Okay. So the top left entry of this 3 by 3 matrix is partial n1 partial x multiplied by partial n1 partial x plus partial n1 partial y partial n1 partial y. Okay. That's just the first entry. 8 more to go. Okay. Next entry, I'm gonna go across the row just to make sure I have enough horizontal space. Okay. We have partial n1 partial x, partial n2 partial x, plus partial n1 partial y, partial n2 partial y. And then the third entry in that first row is partial n1 partial x, partial n3 partial x, plus partial n1 partial y, partial n3 partial y. Okay. I wrote it a lot neater in my notes, trust me. But hopefully you can start to see a pattern emerge, right? So every term or every expression here has 2 x derivatives multiplied by each other plus 2 y derivatives multiplied by each other, and then the indices for those correspond to whatever row and column that's in, right? So row 1, column 1, we have n1, n1. Row 1, column 2, we have n1, n2. Row 1, column 3, we have n1, n3. Okay, so you can basically kind of carry that pattern kind of through. All right, so we go to the second row. Second row, we have partial n2 partial x multiplied by partial n1 partial x plus partial n2 partial y partial n1 partial y. Okay. Next entry here, we have partial n2 partial x partial n2 partial x plus partial n2 partial y partial n2 partial y. And then third entry, third column in the second row, we have partial n2 partial x, partial n3 partial x plus partial n2 partial y partial N2, or yeah, partial N3, excuse me, partial Y. Okay. All right, and then the last row. So the last row is just following the same pattern. So we have partial N3, partial X, partial N1, partial X, plus partial N3, partial Y, partial N1, partial Y. Okay. Okay, partial N3, partial X, partial N2, partial X, plus partial N3, partial Y, partial N2, partial Y. And then we have the 3, 3 term. So partial N3, partial X, partial N3, partial X, plus partial N3, partial Y, partial N3, partial Y. All right. It's a doozy, I know. So we're just about done for today. We just have to kind of finish up this expression here, okay? So of course, this is definitely the scariest part of the element stiffness matrix. It's the matrix part of the element stiffness matrix, but it's not everything, right? So we do have a few extra terms there that we have to kind of carry over. Okay. So most importantly, we have the K term we have to carry over. Okay. We have the integrals. Okay, that has to carry over as well. We're integrating over dA, and of course we have to bring down the coefficients as well. Okay. So let me just do that really quickly. And so on the outside here, we have W1, W2, W3. Okay. Then we have a double integral over A. Okay. We're multiplying this entire expression by the thermal conductivity K. Okay. And then this entire expression right here is multiplied by the column vector T1, T2, T3 integral over dA. All right, so this right here, let me go ahead and put a box around this entire thing. This right here is our element stiffness matrix. So of course, it looks extremely scary. And if you were to compute this by hand, it would be extremely tedious. But remember that your shape function derivatives here, all the partial n's, partial x, partial n, partial y, they're all constants in this case because our shape functions that we started out with were linear, right? And so in fact, we pre-computed these shape function derivatives up here, right? And so the ideal way to kind of use this is to use a computer, obviously to use a computer code to help you, pre-compute the shape function derivatives. You're going to write kind of 6 lines of code for that, and then just multiply the matrices kind of exactly as we've done in our codes before. Okay. Then you're going to multiply it by K. We're going to integrate over the area, but since everything inside this integral here is a constant, for the most part, the thermal conductivity is a constant. Then you're just going to multiply by area as well. Okay. All right, any questions on this before we wrap it up for today? Okay. All right, so when we come back on Tuesday, yes, our midterm is next Thursday. So when we come back on Tuesday, we'll finish this up. I have one example that kind of shows you kind of how to do this. We'll talk a little bit about Gauss quadrature in 2D. And then after the midterm, we'll be set to talk about isoparametric elements, which is the last major topic of this course. All right, so thank you guys for coming today. I hope you guys have a good rest of your day. Hope you guys have a good weekend, and I will see you guys next week. See you guys. Yeah, have a good weekend.
Thank you.
You, George.